So, what other changes can actually, or what other changes can be responsible for climate change? Well, the next set of changes are these changes that were postulated by a scientist named Milankovitch, and hence they're called the Milankovitch cycles. The Milankovitch cycles relate to changes in Earth's position relative to the sun, as well as Earth's tilt, how tilted Earth's axis is, how oblong Earth's orbit is, and where Earth's axis is actually tilted at, what direction it's tilted in. These are called the eccentricity, obliquity, and precession cycles. The eccentricity cycle deals with how circular and elliptical Earth's orbit is. Obliquity deals with changes in axial tilt, and precession deals with what direction the tilt is pointed in. So let's talk about each one of these in slightly more detail. Okay, eccentricity. I don't know how many of you have taken an intermediate algebra class or a college algebra class where you talked about ellipses. Ellipses is basically a fancy term for ovals. Well, fun fact, Earth's orbit is actually an ellipse, and the sun is one of the two foci of the ellipse. Now, that being said, the eccentricity of Earth's orbit, which is basic fancy word for how far apart the two foci are, and how oblong the orbit is, how oval the orbit is relatively small. But the eccentricity does change over time, causing Earth's orbit to go from more circular to more oblong to more circular to more oblong. And Earth's axis actually does experience a change in its eccentricity. This cycle lasts, or the cycle takes about 100,000 years. And what this impacts is this impacts our distance from the sun. Now, it's worth noting that Earth's eccentricity is never perfectly zero. Earth's orbit is not a perfect circle. But Earth's eccentricity, the eccentricity of Earth's orbit, is pretty low, representing a very circular orbit. So representing a very circular orbit. Okay. That cycle takes 100,000 years. Can that account for as much warming as we've seen in the past 140,000 years? No, it simply can't. So let's see what the next cycle can offer. The next cycle is called the obliquity cycle. This cycle deals with how tilted Earth's orbit is. Earth's orbit is currently tilted at an angle of 23.5 degrees relative to the sun. So 23.5 degrees relative to the sun. This is what causes our seasons. The greater the tilt, the more intense the seasons are. The less the tilt, the less intense the seasons are. The change in seasons can actually cause changes in ice growth because more extreme seasons can actually trigger more ice growth, whereas less extreme seasons can actually prevent ice growth. So this whole process lasts, or this whole cycle takes 41,000 years. Where in 41,000 years, Earth goes from its current tilt to more tilted to less tilted back to current tilt. That cycle takes 41,000 years to complete. And again, that would affect things like how intense our seasons are. This really can't account for climate change either. It's too slow. Okay, third thing, precession. So, have you ever played with a spinning top before? I know you're all Gen Z and Gen Alpha. You probably haven't played with a spinning top. An app has a spinning top or something. Um, or a dreidel or something like that that you just spin and it wobbles around. Well, that wobbling is just like Earth's axis. Earth spins on an axis and the axis wobbles in directions. It's the direction that it's pointed at wobbles. This is called the precession cycle. And so the direction that Earth's axis is tilted in changes over time. Currently, Earth's axis is pointed towards a star called Polaris, or what we refer to as the North Star. In about 11,000 years, roughly halfway through the precession cycle, Earth's axis is going to be pointed in the other direction towards a star called Vega. And that'll be our new North Star. That'll be in about 11,000 years. What this actually impacts is this actually impacts what time of the year we're closest to the sun, what month of the year we're closest to the sun. What's really, really cool is that astronomers have been able to document and track this change so well for so long that the precession cycle is actually baked into the Gregorian calendar. And so if that wasn't the case, but we would start seeing summer in summer in January and winter in July here in the northern hemisphere. But because the precession cycle is actually accounted for in the Gregorian calendar, we actually don't have that. But what will change is in about 11,000 years, we'll be closer to the sun in July and further from the sun in January. Whereas currently we're closest to the sun in January and furthest from the sun in July. So those dates are called perihelion when we're closest to the sun and aphelion more farthest away from the sun, respectively. This cycle total takes 23,000 years. So in 11,000 years will be pointed at Vega. In 23,000 years will be pointed back towards Polaris. Obliquity and precession like a spinning top. So if you've never played with a spinning top before, go outside and touch some grass and play with a spinning top. Okay. The next lesson I'm going to talk about relates to internal forces. No. Next lesson deals with other types of exterior forces, including meteor impacts, which meteor impacts can cause relatively short-term but catastrophic climate change. Famous example, the Chicxulub asteroid that killed the dinosaurs 65 million years ago. And so that's another external forcing that could also cause climate change. If you get a catastrophic asteroid impact that, boom, causes massive sudden climate change. The last lesson that we're going to talk about are internal forces. And so it'll be in the next video.